So hello guys, welcome to Examalist. So in the last lecture we discussed about normalization of free particle and the problems that we are facing. So in this lecture what we'll do is we'll talk about Dirac delta function. So let us start. So consider a function f of x and x. So when x is 0, say f of x is 0. Okay. So when x is 1, say f of x is 1. And when x is 2, say f of x is 4 and so on. So when you are given the following data, then you can easily predict the form of f of x. So of course, f of x will be x squared. It's quite logical. So every function has a form. By form, I mean somehow it is uh, in some, it can be written in terms of x. Once the data is given, you have a form of f of x. But there can be function who may not have form. They have values, but they don't have form. Okay, f of x has a form. It can be written in terms of x by a combination of x square, x cube, whatever. But there are functions that can have no form at all. So let me write one such function. Consider a function f of x whose data is such that the value of f of x is infinity at x equals to 0. So when you are at point x equals to 0, the value of f of x is what? Infinity. And when you are at the position away from origin, so when you are not at the origin, when you are not at 0, then the value of f of x is say 0. So the value of f of x is 0. So this is a function, and this function f of x has no form. Unlike the function on the left hand side, it has a form, but this function has no form. So it cannot be written in any ways in x. So there is no way you can write f of x in terms of x. So these are formless function. They cannot be written in terms of x, but they do have values. This f of x is also written in another style, and it is also has a name called as the Dirac delta function. It has a special name. Or you can write as a delta x minus 0. So the reason I'm writing minus 0 is because to indicate that at x equals to 0, the value of the function is infinity. Can we draw? Let us try to make a graph of how it looks. So consider an x-axis and the y-axis. So let me level them. So this is y and this is x. So with a red line, let us see. At origin, the value of the function is infinity. So let me take a red line and make an infinite spike at x equals to 0, because the value of the function is infinity at x equals to 0, and it is 0 everywhere else. So the only place where I can draw the function is only at x equals to 0. The only way I can draw is make a spike. Look at the red line. I'm making the Dirac delta function. Agreed? So it will go till infinity, up and up and up. And there is another form. So if you are given a Dirac delta function, which can be written in this manner as delta x minus x naught. Agreed? Then this Dirac delta function can be written as, so the value is at x equals to x naught, the value goes to infinity, and at any other place the value is 0. So I hope you understand this. Okay, so this is the same. So the minus x naught says that the value exists at infinity. So let us draw. So make x-axis, y-axis, and so what is the value? Somewhere at x naught. So consider I draw an x naught somewhere around here. So this is my x naught, and at x naught the value of the function is infinity. So I should do what? Infinitely I should take it till infinity. And since it is 0 at any other x, so I cannot draw the red line at any other place. This is the Dirac delta function. So 1 and 2 both are different way of writing the Dirac delta function. Do Dirac delta function has a form? The answer is yes. Although it may not have a form in terms of x, x square, or some combination of x, x square, but it may have a complicated form in terms of say integration. So let me write the form. So the form has contains both the value, so it can be written as this. So Dirac delta function, this is nothing but a Fourier transform of Dirac delta function. Actually this is the Fourier transform, but if you don't know Fourier transform, then just remember that delta of x do have a form, and this is the complicated form. It's a improper integral from minus infinity to infinity. Now in quantum mechanics, let us return to our discussion of quantum mechanics. We had two things. In our previous lecture, we considered a free particle, and we know that a free particle has a definite momentum p. So the wave function of this free particle can be written as this. Remember k is so h cross k is p. This was from de Broglie equation, and you can see psi is equals to a e to the power minus I p by h cross x is the wave function for a free particle whose momentum is known 100%. So when a particle is moving on space, we know its velocity. So if a particle is moving in space at a velocity 10 meter per second, it's always moving at 10 meter per second. So the momentum is exactly known for this free particle, and this is the wave function that you see. So this is the bracket that I'm doing. This is my wave function. Now a is unknown. Actually we don't know the value of a is the normalization constant, and as we saw in our last lecture, we faced a big problem while trying to normalize the wave function and finding the value of a. We faced some problem. Okay, so we'll discuss the solution later on, but how about a particle which has a definite position? So consider a particle is exactly at x naught. So the position of this particle is known by 100%. Okay, as in the case number 1, the momentum was known by 100%. In second case, the particle is at x naught, so the position is known by 100%. Now question is how to write the wave function of this particle. Yes, the wave function of this particle can be used by the use of Dirac delta function. So it can be written as a delta of x minus x naught. Why minus x naught? Because the particle is found at x naught. So this is the wave function of a particle whose position is exactly known. So Dirac delta helped us to do this. However, our discussion was something different. Our discussion was that we need to solve the normalization problem of the free particle. So we assume the look at the wave function for 1, that psi, okay, e to the power minus I p by h cross x. So this is the wave function we tried to normalize and we failed miserably. Now question is what to do, either betray quantum mechanics or make a sleight of hand. See, when a theory works, then the best thing to do is wherever you have problems, try to solve them, or by use of trick of hand, do something to the such that the problem is does not look so bad. We do the same thing here. So what we'll do is consider that is at equation number 1. Okay, so what was the normalization condition? The normalization condition was integration minus infinity to infinity psi square dx is 1. Now instead of assuming 1 on the right hand side, scientists suggested that use Dirac delta function for normalization. So instead of using 1 for the normalization condition on the right hand side, they suggested use Dirac delta function. So now the normalization condition is a bit improved. I mean, some improvement or some changes in the normalization constant equation is required, and some changes in the wave function psi is required. So what is the change in the normalization constant? Instead of 1, use Dirac delta function, that is x dax minus x. Now to get x dax minus x, look at that equation, compare it with this equation, and then you can easily predict the value. So what will be the value? The value will be e to the power I x dax minus x. So can you guess the value of psi? We know that psi square should give me e to the power I x minus x. So the value of psi will be the root over of that. So you have a root over of 1 by 2 pi, and you will get e to the power I k x. Agreed. So you can also write in terms of momentum p if you don't want to use k. For example, look at this. So all you have to do is write h cross below and include an h cross here. So if you solve it, you'll understand. So if this is the wave function, if this is the wave function, if this is the normalization condition in terms of p, then the modification in the wave function is this. Agreed. So we solved the problem of normalization of free particle by making a bit changes in the normalization condition itself and some changes in the wave function of the free particle. So this is how the wave function of the free particle must be written. Okay, so in this way, Dirac delta function helped us to get us out of the problem of normalization of free particle. So in the next course of lecture, we'll discuss more on Dirac delta function and quantum mechanics and everything. We'll also have little bit complicated discussion of Fourier transforms. So please follow my lectures on Fourier transform in the mathematical physics CD. Okay, so x naught, as I said, minus x naught would mean that Dirac delta function has a value at x naught. Anyhow, so I hope you get the point.